So for my project, I did a comparative analysis of Stockfish and AlphaZero. If you don't know, these are chess engines. I really wanted to go over their methodologies and how they performed against each other. So, as a quick introduction to the problem, chess has kind of been seen as one of the original kind of man versus machine problems. And in 1997, IBM's Deep Blue defeated Garry Kasparov, chess world champion at the time. And this was really a landmark moment. Not only was it the first match that um, a computer had beat a human, it was also the first time Garry Kasparov had ever lost a chess match. Um, it really changed how humans think about the game of chess, as well as um, people saw the ability that machines had. Um, and as a result, chess is kind of seen as a benchmark for artificial intelligence. This is one of the reasons this is true is due to the kind of deterministic nature of chess. Each move has um, a significance towards it. Um, you can't really blame outside factors for losing. It's entirely your fault. And as a result, chess really has highlighted the evolution of these statistical models. In order to kind of demonstrate this problem, I think it's really important that I just do a quick overview of kind of the fundamentals of chess, just to make sure everybody's on the same page. So chess is made up of a board. It's an 8 by 8 grid, black and white squares. There's six different pieces, the king, queen, rooks, knights, bishops, and pawns. And the main objective of the game is to checkmate the opponent's king. Um, and each of the moves are worth different values, and I'll go a little bit more into that more later, but this is largely due to the difference in piece movement. So about the relative values of pieces. So each piece is normally assigned a value. So pawns are assigned a value of 1, knights a value of 3, bishops a value of 3, rooks a value of 5, and queens a value of 9. The king, however, it's really difficult to kind of assign the value of a king because if you sacrifice all your pieces but two and then you checkmate the king, then you win. So um, kind of checkmating the king is kind of seen as worth more than the piece value. Um, so these scores help to denote positional advantages. For example, so it's normally called centipawns. It's how you denote these positional advantages. So +1 would mean that white's ahead by a pawn, but most positions, let's say they're equal amounts of value, equal amounts of material value, um, there might be a slight advantage in terms of centipawns. So maybe zero point 0.3, which would be a third of a pawn, for example. But the thing is that these piece values can really change. They can change a lot depending on the position. So take this example. Um, material is equal, but white has these two rooks on an open file. So these rooks conventionally are normally only worth 5 pieces, five points. But in this example, because they have all of this open space ahead of them, they might be worth, say, 5.15, which isn't a lot, but as a result, white is winning according to Stockfish. So another thing that's really important to consider is how we rate these chess engines. So chess is normally rated on an ELO. So beginners are between 800 and 1200. Intermediates between 1400 and 1800. Grandmasters are 2500, and then these chess engines are all the way up to 3500, even 4000. Um, so there's really more in common between the best chess player and you or me, and we're closer to the best chess player in the world than these best chess players are to something like Stockfish or AlphaZero. So how do these engines evaluate positions? Basically, these engines are maximizing a score function. These could be down to piece values and positional factors. They're searching for an optimal sequence of moves. So the two methods used, the two different approaches used. So Stockfish uses more of a tree search based method, while AlphaZero uses neural networks and Monte Carlo tree search. So first, I want to dive a little bit into the methods that Stockfish uses. So Stockfish is an entirely open source chess engine. There's been hundreds of contributions, but the key component that Stockfish contributed is the alpha beta pruning and minimax search. And while this algorithm um, originally came from checkers in like the 1960s, it's been adapted and optimized um, in ways that actually turn into a great chess engine. So I want to briefly talk you through this visualization of alpha beta pruning. So for this example, due to being able to fit a tree on a slide, um, pretend there's only two different evaluations. So for example, in this example, you can only move two pieces, so you have two choices. So it's a bit easier to understand working the opposite way. So black basically has two options. Black is trying to minimize the score function. So black wants the minimum value and white wants the maximum value. So let's say it's white's turn, but we're going to stop. There's a depth of 3, for example. So 1, 2, 3. And we're going to stop on black's turn. So black has these two options, evaluation of -1 and evaluation of 3. So white is trying to maximize this algorithm. So white's going to opt for the value of 3. Um, Then we'll do it for the same thing for the other side. White's trying to maximize it, picks the maximum value, 5. White picks the value of 5. So on and so forth. Black is then trying to minimize this side of the tree. So it's going to pick between 3 and 5. It picks the minimum, which is 3. And then pretend I just explained this side of the tree. White is trying to maximize between 3 and -4. White chooses the 3, obviously. And therefore white evaluates this position at a maximum value of 3. So that's just kind of a quick overview of the algorithm. Yeah, and just mathematically, I'm not going to go too far into this. White's trying to maximize utility function U. Um, the game tree is traversed using depth first search, so opposite way, but it's easier to explain going the other way. Um, and really importantly, Stockfish normally searches to a depth of 20, so basically 20 nodes down the tree. And the pruning, or kind of removing, in other words, removing trees that it doesn't need to go down, reduces complexity from O of B to the D to O to the B D over 2. So it's very, very efficient to prune. Another method that Stockfish employs, this is only kind of a recent development in 2020 after AlphaZero was created, um, was the method called efficiently updatable neural networks, otherwise known as NNUEs. So this method was originally developed for shogi, which is Japanese chess. Um, and these neural networks are basically optimized for CPU execution. And this is kind of due to the problem with chess engines is the evaluation needs to be very, very precise and very, very fast in order for chess engines to go farther down the tree. So there's kind of this trade-off is how precise can you evaluate the position and how deep you can search. So that's kind of what motivated this method. So basically what NNUEs take, um, just kind of mathematically, takes an input vector X, has L hidden layers, weight matrix W, bias vector B. It takes some sort of activation function, and Stockfish it uses the sigmoid, which is like logistic curve. Um, and then the evaluation value is just a 1 by 1, so just a scalar. Um, I'm just going to kind of move on. Don't want to get too nitty-gritty, but the really main thing that I want to highlight is that um, the output function, or the output of sigma of x, is only takes 3 different values. And really the reason behind this is to avoid floating point values when running the neural network. Floating point values are very, very tedious computationally, so only having to deal with integers um, or three values is much more efficient in terms of CPU, running neural networks on a CPU. And then really quickly, so NNUEs take an input vector, which is basically a bitboard based encoding. A bitboard's a data structure that's basically optimized for an 8 by 8 structure, where each square represents a bit, so it's super, super fast. And whether or not a piece is on the square, um, it will get a 1 or a 0. And then you do this n times. Um, a quick note about the NNUE architecture. It takes 768 sparse inputs, so it's is kind of an adaptation of the bit board. I couldn't find the exactly how they computed it, but this is kind of done over numerous tests. It's changed lots and lots of times, but this is what it's currently at. Um, there's two hidden layers, a hidden layer of 8 and a hidden layer of 32 neurons, and then the output is just the centipon evaluation. So next, I want to talk about the methods used in AlphaZero. So AlphaZero is basically it's a reinforcement learning algorithm where these machines are learning chess, Go, Japanese chess entirely through self-play. So it learns strategies entirely from scratch, and you're only giving it the rules when you're training these algorithms. And while it was really cool to see AlphaZero's improvement in chess, it was the first computer program that was able to beat um, human players at Go. So it's more commonly famous for that. It was the very first computer algorithm to do that. So it's a neural network where S is you give it S, which is the current state of the board, and then as an outcome or as the output, it gives you the move probabilities and the expected outcome of the match. So it learns these probabilities entirely through self-play, and it adjusts these outcomes during training. So it learns these through simulations. For example, it was able to beat Stockfish in nearly 8 hours. Um, and it selects moves um, based on the search three due to three criteria. Um, it mainly searches for moves that intuitively thinks it will be good. In other words, moves that it thinks it has a high probability of being good over the course of simulations that it's already ran. It will go deeper and deeper down those lines for the moves that it believes to be good. So, for example, if you hink queen on the first move of a line, it would assign a move probability of 0 to that line because you don't want to give up your queen. That's your most valuable piece. Um, and then based on these move selections, if it's a good move, it'll probably output a higher average value of wins um, based on moves it made in similar positions. And so it generates this probability distribution. The game outcomes are mapped as -1, 0, and 1, -1 a loss, 0 a draw, um, 1 a win, and then theta is adjusted by gradient descent on the loss function. So I want to quickly go over the results in this of AlphaZero versus Stockfish. This is before Stockfish implemented the NNUE as it kind of adapted that algorithm from AlphaZero. One also thing that is important to note is that these matches are kind of started from random positions. Chess engines have a tendency to just make quick draws, they're averse to risk. So they'll drop it into a random position in which one side might have an advantage or disadvantage. These are normally chosen from things like famous games or unique positions that the researchers want to study. So as you can see, AlphaZero kind of wiped the floor with Stockfish. AlphaZero won 25 times as white, and they drew 25 times. And then AlphaZero won 3 times as white and drew 47 times. Or as black, it won 3 times and drew 47 times. So there's kind of two main takeaways from the study. AlphaZero kind of prioritizes sacrifices and positional play. It's despite being better, it's easier to explain AlphaZero's moves. It kind of has this aggressive style, um, whereas Stockfish is simply picking the best move off of probabilities it makes. So AlphaZero's moves are often more explainable, which is kind of strange considering it's a tree-based algorithm versus a neural network. So it's normally the other way around, but interesting example. So I want to take one example from a game just to kind of illustrate this. So it's the material is entirely equal, but AlphaZero is playing as black. So AlphaZero decides to just sacrifice this knight. Um, After sacrificing this knight, it's going to pick up one or two pawns um, in return, but it, black's going to gain access to the king. So it's kind of this weird dichotomy in that it prioritizes piece activity and really opening up the position, getting its pieces active rather than just the total number of pieces, which is kind of like a very non-chess engine-like approach, surprisingly, at least in the past. So there's kind of this paradigm shift as a result. AlphaZero learned entirely through self-play. It was a completely novel strategy. There was really no reinforcement learning algorithms that had um, been developed using these methods, and it kind of really suggested this trend that kind of maybe the path to artificial general intelligence might emerge from adaptive learning, so learning like humans do, which is really, really interesting. Um, so just kind of in conclusion, Stockfish is more excels more on the brute force calculation level, um, but AlphaZero has more of this like human style where it sacrifices pieces, likes to push its pawns, plays very, very aggressive. Um, and overall, it's just very, very interesting to see it as a dumb human. But it kind of shows that the future of chess engines might involve kind of a hybrid approach. Um, and maybe there's places to use both methodologies. Unfortunately, AlphaZero um, discontinued developing its model after it wiped the floor with Stockfish. But um, yeah, so that's all I've got. Thank you so much.